This month's tip is, don't be tricky with GD&T.
Let's say that the primary datum feature on this part is going to be this smaller diameter, which will establish an axis. The secondary datum feature is going to be this face, and I want to control its relationship back to the axis. It's a 90-degree relationship, so I want to keep it perpendicular. According to the Y14.5 standard, there are several different controls that I could use in this case. I might consider using profile of a surface. Now, profile of a surface is usually used to locate features, but in this case, since there's only a 90-degree implied basic angle here, it could be used to give me that tolerance zone I'm looking for. However, on a more complex drawing with a lot of basic dimensions, and because of the rule of simultaneous requirements, I might end up getting more than I bargained for with the profile of a surface. I could use total runout, and that would control the perpendicular relationship of this feature to the datum axis. I usually think of total runout on cylinders, but it would work here. I could use perpendicularity, which, is what I was after in the first place. Or, according to the 2009 Y14.5 standard, I could replace perpendicularity with angularity. The standard says there's an implied 90-degree angle, and it's really giving me the same control as perpendicularity. However, whenever I see that angularity tolerance, I start looking around the drawing to see if someone slipped in an 89.9-degree basic angle someplace. So there is overlap in the geometric tolerances, and in this case, I would have several choices. We have 14 geometric characteristic symbols in the Y14 standard, and then with the modifiers, it takes us up to about 25 symbols, which I think is just about right. These symbols are very descriptive and tutorial. They sort of guide the reader. I don't want to go to too few symbols because then people would have to assume too many things. And I don't want to go to too many symbols, which is what we're seeing today in the development of the ISO standards, where they're looking to have about twice as many symbols as we use for geometric tolerancing. In this particular case, I wanted to control the feature's perpendicularity, so why not just say perpendicular to the datum established by datum feature A.
Hey, save the tricks for your next magic show, and remember, at Techies, GD&T rules. I'll see you next month. The 2009 revision of the Y14.5 standard has added a chart that shows various datum features, their datum feature simulators, and the degrees of freedom that they may constrain when the feature is a primary datum feature on a regardless of material boundary basis. This series of tips illustrates each of these datum feature types using video clips from our computer-based training course.
Let's start with a plane. Here I've identified the lower surface of this part as datum feature A. The simulator might be something like a granite surface plate, and it's establishing a datum plane. Now, a datum plane, if it's primary, arrests 3 degrees of freedom. 1 translation, and you can see this part wouldn't be able to move up and down anymore, and 2 rotations. Rotation about 2 of the axes. Sometimes, though, it's easier to understand the degrees of freedom being constrained by thinking about what degrees of freedom have not been constrained. If we look at this part resting on a surface plate, the part could still move left and right and front and back, and it could still rotate on the plate. Since there's 1 rotation remaining, 2 must have been constrained. And since there's 2 translations remaining, 1 translation must have been constrained.
The 2009 revision of the Y14.5 standard has added a chart that shows various datum features, their datum feature simulators, and the degrees of freedom that may be constrained when that feature is a primary datum feature on a regardless of material boundary basis. This series of tips illustrates each of these datum feature types using video clips from our computer-based training course.
There's another way to establish a plane, and that is if we're establishing a center plane.
Notice that my datum feature identification symbol is lined up with the size dimension. When it's lined up with that size dimension, it says I want the center plane of this feature of size. So I need to grab it or close in on this with two parallel planes at minimum separation. Now that would be the unrelated actual mating envelope. In practical terms, it might be an inspection vise. And then by indicating off the faces of the jaws of the vise, I can determine where a center plane would be. And because we're establishing a plane, once again, I'm going to take away two rotations, so one will still be remaining. And you might say, wait, if I grab this in a vise, it can't spin like that. Well, don't count friction. Okay, so it could spin like that if you just made contact and didn't clamp down tight on it. And I have two translations remaining. It can move left, right, and it could move up, down in that vise. We started with 3, 2 are remaining, so I must have arrested or taken away one translation. So here's a centering vise that you could buy for $259 from the Enco Corporation, at least at the time I was making this video, that will close in and center up all the time if you have this set up in your machine. Or here's a milling vise, and I would have to indicate off the surfaces and then center up. Now often I'll have folks from the shop say, yeah, but I don't want to do that. And I understand that, but if I need symmetry, this is what you need to do. If I have a slot, I still can get a center plane. I could fill it with the largest stack of gauge blocks that will fit in that slot and then indicate off the surface of the gauge blocks.
Did you ever wonder what really goes on inside a design engineering office? Well, the designers and engineers are working very hard trying to meet some deadline to release the drawings. Then the drawings go out to the people that are going to use the drawings for a drawing review. But by then, it's too late. They ask for changes that'll help out with the production or inspection of the parts, but engineering is usually off doing something else and doesn't have the time to go back and make those changes. This ends up creating an adversarial relationship between design and the folks that are using the drawing. Consequently, production, inspection has to develop their own tribal knowledge, which a lot of people call troubleshooting, at the startup in order to make the parts in spite of the drawings. Many people wait until they find a problem and then fix it. And by then it's too late. So what's the solution? Well, you pull together the multifunctional design team. And I don't mean just designers and engineers. You pull together the people that are going to use the drawing before the drawing ever gets made, before the datums and the geometric controls have been added. Design produces the drawing, so they're the supplier of the drawing, and whoever receives it becomes design's customer. So not only does design have to make sure that what they put on the drawing will satisfy design intent, but it has to be producible and it has to be inspectable. So we must meet design intent, it must be producible, and it must be inspectable. The way you do this is to pull together the team and discuss how the parts are going to be assembled, what the critical features are, what kind of tolerances can actually be held, what the inspection methods will be, and then the answers to those questions are documented using datums and geometric tolerances. It's time for drawing previews at the model stage. Don't wait until the drawing's made and then have a review. I often refer to the geometric dimensioning and tolerancing tools as tools in your toolbox. Of course, like any tools, if you don't know how to use them, they won't do you much good. So let's take a look inside the toolbox. In my toolbox, you'll find that there are 2 trays. The top tray is for those tools that I use most often, and those are the locating controls. So that would be position for features that have size, or run out for either circular or total for the coaxial features, and profile of a surface, which can locate any surface on any feature. So profile of a surface is like the duct tape of geometric dimensioning and tolerancing. Occasionally, though, I have to control the orientation better than location. Now, location gives you orientation for free, always. But if you need to control the perpendicularity, parallelism, or angularity better than the control you're getting with the locating controls, you could refine with one of these. And down in the bottom of the toolbox, you'll find the form controls, which aren't needed very often because you get form for free with profile, with the runouts, and sometimes with the orientation controls. And then there are a couple of tools that aren't in my toolbox anymore, and those are concentricity and symmetry. Sure, I want features to be symmetric or concentric, but I can achieve that using position, profile, or in the case of concentricity, even with the runouts. So concentricity and symmetry have gone the way of the old slide rule. Seemed like a good idea once, but we really don't need it anymore. This is tip 4 in the series of 6 tips on types of datum features and the degrees of freedom they may constrain. Where a cone is used as a primary datum feature on a regardless of material boundary basis, it can constrain 5 of the 6 degrees of freedom. Once you grab a cone with a theoretical datum feature simulator, the only thing it can do is rotate. So far in this 6-part series, we've seen how the degrees of freedom may be constrained by planes, spheres, cylinders, and cones when they are the primary datum feature. This month, we see what a linear extruded feature or pattern of features may constrain. Here's a clip from our computer-based training course. Linear extrusions also take away 5 degrees of freedom. Now, don't confuse this with an extrusion process. There's lots of different features that can be made in many different ways that qualify as linear extrusions. Although when I think of a linear extrusion, I think back to the old Play-Doh Fun Factory days where we would extrude Play-Doh out through different shapes. But a pair of holes could qualify as a linear extrusion. The only thing these features can do is translate. We've taken away all the rotations and 2 of the translations. This shows the datum feature simulator and a part that I might put in that simulator. Some people like to look at this as what we've defined for datums. And we've defined a plane in this case and a line. And that plane and line constrain 5 of the 6 degrees of freedom. We know a plane constrains 3, and the line then could constrain another 2. I have a pair of holes here that I'm using as a datum feature. Notice it says 2x, so whatever follows that applies to both holes. So we have the size and the position tolerance to tie them together, and now I'm calling them out as datum feature A. So the 2 holes acting together establish our datum, and these are a linear extrusion. So far in this series of 6 tips, we've seen the degrees of freedom that may be constrained by planes, spheres, cylinders, cones, and extruded features when they are a primary datum feature on a regardless of material boundary basis. This month, we see that a complex feature or pattern of features may constrain all 6 degrees of freedom on the part. Here's a clip from our computer-based training course. And the last category we're going to talk about are the complex features. Now, a complex feature could be some very complex curve that could constrain all 6 degrees of freedom. Or it could be something as simple as this shape, which also constrains all 6 degrees of freedom. So if I have this called out as a primary datum feature, there wouldn't be a secondary or tertiary datum feature because there'd be nothing for them to do. Once again, if we want to look at the datums that are established by this, there's a center plane down through this, there's an axis just like we saw with the linear extrusion, but I also have a point because of the taper in this feature. It's going to restrict moving up and down, and that's what the point is doing.
I'm frequently asked if a geometric tolerance is legal or illegal. The first thing I do is look at the title block and notes to see if a revision of the ASME Y145 standard, a corporate standard, or some of the many ISO standards have been referenced. If not, I have to say that I do not know if the GD&T is according to the standard. Applying a standard in the USA is voluntary. Each company must decide what standards, if any, they want to follow. If the drawing references a standard, the rules of that standard apply. If no standard is referenced, there are no rules, and the drawing may be interpreted in several different ways. Here's an example of how to state the standard that the drawing is made to. Down here in the notes, it says that dimensioning and tolerancing is in accordance with ASME Y145-2009. So all of the rules that are found in this Y145 standard apply to this drawing. Notice it says in accordance with. I like that a lot better than based on, which I see on many drawings. You know, if I watch a movie based on the life of somebody, I know there's a lot of fiction in there. So saying you're in accordance with just seems to be a little cleaner. If you want your drawings to have one clear meaning, make certain that it's clear what rules apply. There are no GD&T police that will arrest you for applying an illegal callout, but there are rules that may be contractually binding when a standard is referenced. Here at Techies, GD&T rules. Often two holes are used as datum features. I've had several requests to explain just how the datum reference frame is related to the holes. In this tip, I'll show you a simple example, and in our next tip, I'll show you what changes if the holes are on a diagonal. All parts in space have 6 ways they can move around, known as the degrees of freedom. Our manufacturing, processing, and inspection equipment has planes, and when we use 3 of those planes that are mutually perpendicular to measure from, it's known as the datum reference frame. The idea is to select features on the part and align them to those planes. On this part, we've selected datum feature A as that surface. So we want to take that surface, especially if it's in an inspection setup, and align it to a measurement plane. When we do that, that will constrain or arrest 3 of the 6 degrees of freedom. Then we would select another feature such as one of the holes as datum feature B. We would then use the axis of the related actuating envelope of that feature and align to that. Now that is actually the intersection of 2 more planes that are at right angles to the first one and to each other. Now we use datum feature C to orient those planes because we have an origin, but the part can still rotate. The axis at B only took away 2 of the degrees of freedom, so C takes away that last degree of freedom for us. You can't always follow the standard exactly. The difference between the requirements of the standard and what you do causes uncertainty. Uncertainty is always present. We just try to minimize and manage it because at Techies, GD&T rules. I'll see you next tip. The first tip in this 2-part series on using 2 holes as datum features showed a simple part. The primary datum feature was the back face, and then we used this hole as our secondary datum feature, and this is our tertiary. That gave us a horizontal datum plane and a vertical datum plane to measure from. In this tip now, we have put the holes off on a diagonal. Remember what we're doing is we're taking 3 mutually perpendicular planes in our processing equipment and we're aligning the part to those planes using the datum features. So the intersection of your second and third datum planes will intersect at the axis of the hole. That's our datum feature B. And then we use datum feature C to orient the planes of the datum reference frame. Now this is awkward many times for measurement, so we've added a 30-degree basic angle, which allows us to have some auxiliary measurement planes. It doesn't add any tolerance to the drawing, it just makes it more convenient then to measure, so you'd rotate your setup 30 degrees. Keep in mind, these are basic dimensions, they don't have tolerance, and as long as we use basic dimensions, we can translate and rotate so that we can make it easier for folks to measure. I'll see you next tip, and remember, at Techies, GD&T rules. If a drawing does not use datums and geometric tolerances, it's nothing more than a cartoon. About once a month, someone sends me one of these cartoons and asks me what it means. This tip is about one that I just received. If you want to see an extended video of this tip, be sure to sign up for our secure premium site. Now here's your tip. I continue to be amazed that there are still drawings out there like the one shown here, where there's no datum features and there's no geometric tolerances, and people actually think that this general tolerance will do the job. I don't know how to set the part up. I don't know what my origins of measurement are. I have lots of features to choose from. And some people argue, well, I know what they want. And sure, you know what they want. The trouble is, parts is parts. We can't make perfect parts. And I don't care how good the machinist or the tool maker is, parts distort due to stress relief and heat treat and on and on. With just a few mouse clicks, I can create a drawing that takes away all these problems. Now I have datum features that establish the origins of measurement. I have position on the holes, I have a general profile that locates the surfaces, and this part is completely defined so that we know how much I can be off from perfect. So when you see a drawing like this in the future, my recommendation to you is run as fast as you can. Don't try to work with this. It's incomplete. Please don't bother asking me to interpret your cartoons. But if you want help making drawings that have one clear meaning, give us a call at Techies. Because at Techies, GD&T rules. I'll see you next tip. This tip, like many in the past, was inspired by one of your comments. For extended video with a more detailed explanation of this tip, be sure to sign up for our premium site. Last month's tip inspired some questions, and one of them was, don't you need half dimensions on this drawing? Well, for a dimension like the 60, it's implied centered on the datum center plane. And so the answer is no, I don't need a 30 dimension here. If you want to put it in, it's not wrong, but I really don't need it. However, down here on this slot, where I now have a 20 plus or minus 0.1, I have made this slot a feature of size. And it would be wrong to add this 10 plus or minus 0.05 for a couple of reasons. One, by saying 10 plus or minus 0.05, I'm telling you I really don't want the slot centered. You see, I'm holding this side of the slot tight within the plus or minus 0.05 and giving more tolerance to this side of the slot, which would allow it to be offset. So it's not only not what I want, it's flat out wrong. This 20 is a feature of size. To locate features of size, generally we use position tolerance. And so this is a corrected drawing on the right. If you did go with this 10 plus or minus 0.05, another question I would ask is, what am I measuring from? Is there some plane between these two holes that they want me to measure from? Or is it the center plane established by this width, datum feature B? And some people say, well, that's the datum feature. Yeah, but this doesn't reference the datum feature. And I don't know what the precedence is. Is B supposed to be used as primary or secondary? This drawing doesn't tell you. So please don't use those half dimensions, especially on these tolerance dimensions like the 20. Do it the right way and control its location using position. And stop burying your head in the sand with those old methods. Your comments really help advance our site, so keep them coming. My tips and responses are always in accordance with the Y14.5 standard because, you know, at Techies, GD&T rules. I'll see you next tip. GD&T can be so simple if you'll just remember the hierarchy. This tip is about a drawing made by someone who didn't remember the hierarchy. If you want to download the PDF or see the extended video of this tip, be sure to join our premium site. Now, here's your tip. I recently had a drawing that looks like this sent to me, and the person who sent it was concerned about the orientation of these four fins relative to the datum axis and to one another on this weldment. So they used parallelism. They forgot about the hierarchy of geometric tolerancing. Folks, once you establish your datums, your origins of measurement, you need to locate everybody else. The part that you could end up with might be like this one. I know you're saying, well, that doesn't look anything like the drawing. But it does meet the requirements of the drawing to be parallel to the axis established by datum feature A. There's only one geometric tolerance that locates surfaces, and that's profile of a surface. So the person should have used profile of a surface, 4x, and that would have not only controlled where these fins are on the part, but also their orientation to the datum axis and to each other in this pattern, and their flatness and straightness. Now, if they need for the fins to be oriented better than the profile of 0.4, you could certainly add a refinement. That's the hierarchy. You start with location, then you could add a refinement for orientation, or if you needed for the fins to be flatter or straighter, you could certainly add that. Locate first, and then refine, but only if necessary. What could be simpler? Follow the GD&T hierarchy and remember the GD&T rules. I'll see you next tip. Thanks, Wendy. We have this new Y14.5 revision dated 2009, and there's so much new in it. Let me just show you a few of the things that are new. We have 7 new symbols in this revision. There's an independency symbol that unlocks Rule 1, unequally disposed for the profile tolerances, an all-over symbol, continuous feature, movable datum target, translation modifier, and the spot face because of a lawsuit. We can customize our datum reference frameworks. This cone's apex would be way out there. That would be one of the origins. We can move it up here to the space where I might be setting the tool in this tool holder. We can use collections of features that you find in molded plastic parts and sheet metal parts to act as datum features. Like on this sheet metal track, I've called out these little bumps as datum feature A because that's how the part works. On this complex shape now, this is back for a cell phone, I can use that complex saddle as a datum feature. They've expanded the composite tolerancing in position and profile. Here we're seeing several tiered composite profile. And my favorite, the Y14.5 standard ties in with the Y14.41 standard, which allows us to embed our geometric tolerances in our 3D model. You know, there's so much to cover in a tip. Way too much. Well, guys, we just went through a day of being updated on the Y14.5 standard to the 2009 revision. What do you think?
Well, I guess looking back at it, the profile controls are kind of a big thing for me. They really expanded the surface profile section. The addition of non-uniform zones to smooth transitions between profile control zones is important. It's a new way of documenting it. They've included an all-over symbol where we used to have all around to control the profile around a contiguous geometries. Now we have an all-over symbol. It supports general surface profile tolerancing, which has been a real big issue for moving towards solid-based design and manufacturing. So it's a big step forward in that way. They've also expanded composite controls to include pattern controls with surface profile.
And Frank, you were saying something about it appears that the standard has been revised to keep up with technology.
I think it has. As technology's changed over the years, CMMs have gotten better. We can measure tighter and tighter tolerances. CNC machines have gotten better. We can achieve tighter and tighter tolerances on parts. So therefore, our standard, Y14.5 in 2009, is trying to accommodate that. We've expanded datums quite a bit so we can use these irregular shapes, these irregular features as a datum feature.
Like with sheet metal parts, a lot of molded plastic, they don't have regular features of size.
That's correct. A lot of the different shapes you see in castings and powdered metal parts, that we're now able to utilize those different shapes as datums. Wasn't available before.
The one problem I always had was most of the default rules can be overridden in one way or another, but we never could override datum precedents. And now with this customized datum reference framework, we can override datum precedents to better reflect how parts really work.
The other thing that we've done is we've added new symbols.
How many are there?
I believe there's 7 new symbols, but the one that stands out for me is the principle of independency symbol. Instead of
we had to write a long note.
Instead of having to write a note about that, we don't do that anymore. Now we have a symbol that says we want these two features to be unlocked from rule number 1. So I don't have to worry about form or size controls form anymore.
Yeah, when you have a feature of size with a fairly tight size tolerance, but it's a really long feature, rule 1 became pretty impractical.
We've got the new symbol translation modifier, which allows you to shift the datum feature simulator into place, and movable datum targets. These are important for industry because it reflects their actual practices, and there hasn't been a way to do this previously. So it reflects, again, real technology, the way that the world is working, the way manufacturing is working. So it's kind of catching up with the standard.
We used to have these elements within a fixture that would slide to contact the part, but there wasn't a good way to actually state that on the drawing. And I also think there was some confusion in the 1994 standard between the standard itself and the math standard. There was a discrepancy there, but now that's been cleared up by use of these new symbols.
Another new symbol is continuous feature symbol. Many times you have a feature that's interrupted, and we know in manufacturing process they're going to machine the whole surface of the whole diameter and put undercuts in there. Before, if we wanted to put a form control, we'd have to put it on each of those diameters where all these interruptions were. Now we have a continuous feature symbol. We can just treat them as a single feature of size, and then rule number 1 applies. We eliminate a call out on those things.
Nice.
They've finally addressed the spot face issue as well. Spot faces and categories used to be treated the same with the same symbology, and they've recognized now that the root diameter of a spot face is really the critical thing, and the radius is defined beyond that in the walls. So they've addressed it with a new SF category spot face symbol.
There was actually a lawsuit that Frank and I were involved with that got into that. A lot of money was involved because they didn't understand what a spot face really is. That's been cleared up now.
Another new symbol is the unilateral or unequal symbol that we use with profile, Jim.
Circle U. I'm so used to using it by writing into addendums that I've gotten used to it. Yeah, it's a great symbol to add in.
With everybody going to solid modeling, the old technique of having an unequal bilateral tolerance or a unilateral tolerance for profile was to put phantom lines on model. Well, in many cases, those phantom lines are not associative, so when you move the model around, you have these phantom lines sticking out here in midair. A technique in 14.5 now, it came from 1441, we brought it over, was to use a U symbol, which means unequal or unilateral, and it saves us from having to put those phantom lines on the model.
So in addition to introducing new concepts and new symbols, the standard has been brought up to speed with the other standards that had been revised since 1994.
As well as expanding some of the concepts, which we've again done with profile, where we're seeing the 3-tiered composite now.
You know, the other thing I noticed is that virtual condition on a datum used to be very confusing. People would say, what condition is your condition in? And now by using boundaries to explain how to work with the datum simulators, it makes a lot more sense and takes the confusion out that we had with virtual condition when applied to datums.
Yes, and there's some new terms, and along with that we have maximum material boundary and list material boundary, so when we see the modifiers on the datum references, now they all have a common term.
So there's a lot of things that have changed in the standard. We have new concepts, we have expansion of principles, we have brought it up to date with the other Y14 standards. And in about a day's time, you too can be updated to this 2009 revision of the Y14.5 standard. This tip is for all those folks who think they have to really spell out on the drawing what they want, for those who don't know the Y14.5 standard. The geometric symbols that you see popping up in this video are all made with the Techies GD&T font that you get for free when you subscribe to our premium site. Now here's your tip.
When you have an issue like this, there are a couple of ways that you could solve the problem. You could use a belt, or you could use suspenders, but you don't need both. In a recent tip, I had a drawing that had some dimensions that were implied centered on the datum center plane. And I had someone contact me and insist that I add half dimensions for the people who really don't know that there's this implied zero basic, and that I can imply that these dimensions, like the 88, the 60, and the 20, are implied centered. So I did that. I started adding the dimensions that person had suggested, and then I thought, gosh, there's a lot of other things that are here by default that I suppose I should add, like the form controls because of rule 1, and with flatness you get straightness, and perpendicularity you get flatness and straightness, and with the position you get orientation, and with the profiles you get a whole lot of other controls, and I explain these in great detail on the extended video that you find on our premium site. Bottom line, though, that if you start to write down the things that are default in the standard, the drawing starts to look like this. So you can have a nice clean drawing like you see over here on the right, or you can make your drawings like that if you've got a lot of time on your hands for the people that haven't bothered to learn how to read prints. It's up to you.
If you're going to be in the business of designing, making, or inspecting parts, learn to read the drawings. That means learn GD&T in accordance with the Y14.5 standard, so we don't have to waste a lot of time holding your hand. This is today's print reading, but you need to understand the GD&T rules. I'll see you next step. Some of you are holding off moving to the 2009 revision of the ASME standard. I hear all sorts of excuses why. We can't afford the training, our suppliers won't understand our drawings, our CAD system doesn't have the new symbols, and on and on. Look, the only people who like change are web babies. I get that. Let me assure you that the clarification and benefits of going to the latest revision far outweigh the perceived negatives. This tip will show you that your drawings do not have to look any different if you upgrade from the 1994 to the 2009 revision. Yeah, there are 7 new symbols, but you don't need the symbols to say what you mean. If you are a premium site member, the premium video of this tip will show you how to say what you mean without using the new symbols.
In the 1994 standard, in section 3.2, we're told that you can always use notes. Situations may arise where the desired geometric requirements cannot be completely conveyed by symbology. In such cases, a note may be used to describe the requirement. So we have these 7 new symbols, but we can handle most of them with notes. The circle I replaces a note that we used to put on our drawings to override Rule 1, which was perfect form at MMC, not required. The double circle where the leader breaks means all over, which has the same meaning as a general note. It's an unless otherwise specified application, usually for profile of a surface. Continuous feature is something that we can do using position or profile without a datum reference. We used to do it in the composite callouts, and now it's fine to use position or profile without a datum reference where you have a continuous feature. So we really don't need that symbol. It's just a shorthand. The movable datum target symbol came out in 1996 in the Y14.8 standard. So if you really want to use that and you don't want to do it by note, you can just reference the Y14.8 standard. Spot face. It's better to show the dimensions for the spot face so everybody's really clear on what you mean, because the subtle difference between spot face and counterbore can cause lawsuits. Datum translation symbol is one that's rarely needed, and you can handle it with a note very similar to the movable target symbol. And the U in a circle is something that first came out in 2003 in the Y1441 standard. So you can reference the Y1441 standard or use the phantom lines to indicate unequal or unilateral tolerance as we did in 1994. By moving to the 2009 revision, many benefits and clarifications can be realized. There's compatibility with the standards that have been released since the 1994 standard was printed. And the new revision reflects many of the changes that we have seen in our coordinate measuring machine and vision system software. There's clarification of size depending on the function and application. There's many types of size, from local size to the size of the actual main envelope. Mating envelopes have been expanded, so it's easier to understand whether you want a related or unrelated envelope when you're trying to establish a center to establish a datum, or when you're controlling the center axis or center plane of a feature. And the same is true for minimum material envelopes where least material condition is applied. The standard now shows more features that can be used as datum features and explains the degrees of freedom that are constrained when they are used as datum features. Datum shift, which is an area that a lot of people have confusion, has been expanded and clarified. Composite tolerancing has been expanded to include more than 2 segments in a position or a profile composite tolerance. Least material condition applications have been expanded, and the list of benefits just goes on and on.
So, you can protest going to the 2009 revision of the Y14.5 standard, or you can relax and enjoy the benefits that it provides. The most important thing, of course, is to follow whichever standard your drawing is made to, because at Techies, GD&T rules. Some folks continue to confuse dimensioning with tolerancing. They read the first section of the Y14.5 standard, which is on dimensioning, and ignore the later section, which shows how to tolerance the parts. Hopefully this tip will clear things up for some of these folks. On our premium site video, I have included a case study that shows a part that was made when the drawing did not make use of geometric tolerancing.
This is a drawing that is very similar to one that you will find in the first section of the Y14.5 standard. That section is on scope and definitions and general dimensioning, not tolerancing. A lot of people look at this and think, oh, I could just apply a general plus-minus tolerance or apply plus-minus tolerance to these dimensions. And they would be wrong. You could have a plus-minus tolerance on the width of this slot because that's a size dimension, and on the size of this hole, or these 8 holes, and that would be fine. But it's totally wrong to apply a plus-minus tolerance to the 33 or 56, or to these angles which are used to locate these holes. If you do, you could end up with a part that looks something like this. And you would have no recourse. The supplier would be on solid ground because the drawing doesn't say how much you can deviate from the goals. Dimensions state the goal. It's sort of like the bullseye of a target. And then the tolerance is how much you can miss that bullseye by. That's like the size of the target around the bullseye. You have to, as you find later on in the standard, make the dimensions that locate features basic. So you notice I have an untoleranced dimensions or basic note down here. So the 16 and the 6 are not basic because they have tolerances written next to them, as does the 10. But the rest of these dimensions are basic. And then I have to apply feature control frames to control how much the part can deviate from these basic dimensions. Now the part you get will look a lot more like what you were intending to receive.
This tip shows once again the GD&T rules. I'll see you next tip. A very robust method of locating a part in an assembly is to use a hole and slot as alignment features. A couple of bullet nose bosses or fasteners may be used to mate with the hole and slot. These alignment features usually become the secondary and tertiary datum features, as is illustrated in the drawing with this tip. This is a motor housing. Originally, the two halves were aligned using tabs and square holes. This allowed considerable misalignment between the bearings for the armature shaft. By creating two semi-perfs in this part, which are bullet-nosed, and a hole and a slot in this, we were able to greatly reduce the misalignment without adding significant cost. I'm often questioned regarding how to geometrically tolerance the slot in a situation like this. The width of the slot should have a position tolerance with respect to the primary and secondary datum features. The two questions I receive most often are, how can the position tolerance be inspected, and how is the part aligned for inspection? In parts 1 and 2 of this tip, I will address the two questions. In this tip, we'll answer the first one. No matter what you use, the intent is to establish the first datum plane, which is a tangent plane contacting datum feature A. A datum axis is then established using the related actuating envelope. Something like the largest pin that will fit datum feature B that is at right angles to the first datum plane. The part is free to rotate about the datum axis then in order to fit the center plane of the slot within the position tolerance zone. See, nothing to it. Imagine trying to say this on a drawing without GD&T. You'd have to write a long note and still wouldn't be clear. Using GD&T, we can say what we mean with a couple of symbols, and of course, knowing the standard, because we all know that GD&T rules. I'll see you next tip. I get asked all the time how a part should be inspected, and you may have heard me say another tip that it really depends on what kind of equipment you have available. Sometimes fixturing is necessary. Sometimes the datum simulation may be accomplished with basic inspection equipment, and at other times the origin may be established in the software of an inspection machine. They all have their place. I have noticed that many folks, though, are confused or maybe just careless about how to establish the origins of measurement during inspection, regardless of the equipment they have available. The Y14-5-2009 revision of the standard is very specific about how the establishment of a datum reference frame needs to be done. Any deviation will introduce inspection error. Yeah, there's always inspection error, but we should try to keep it to a minimum. This tip illustrates establishing a datum reference frame for a part that uses a planar surface for a primary datum feature, a hole as a secondary datum feature, and a slot as the tertiary datum feature. It helps to keep in mind that the datums are in the processing equipment or the inspection equipment, and the datum features are used to align the part to some or all of the datums in the datum reference frame. So, first, datum feature A is brought in contact with its simulator. The simulator for datum feature B is the largest cylinder kept perpendicular to the first datum plane that will fit the hole, which is datum feature B. The standard calls this the related actuating envelope. Once that is done, the only thing the part can do is spin around the axis of the datum feature B simulator. This spinning, or rotation, is constrained by datum feature C simulator, which is a rectangular block of maximum width that will fit while staying perpendicular to the simulator for datum feature A and centered on a plane that passed through the axis of the simulator for datum feature B. This is another related actuating envelope. These are the rules to establish this datum reference frame. You might choose to ignore the rules, but here at Techies, GD&T rules. I'll see you next tip. Let's end the confusion about datums by using the correct terms. On this part that goes into our clutch brake, this surface is datum feature A, and the bore is datum feature B. These are not the datums. These features have imperfections. The datums exist in our processing equipment. The part is a blob of material. We use gauge pins, angle plates, indicators, etc. to contact the datum features on the part and line the part up to the much higher quality planes and axes that exist in the equipment. When I hear a trainer say, that this is datum A. I cringe. Datum feature A establishes a plane in the equipment. The bore that is datum feature B is used to line the part up with the axes of the equipment. This axis is the intersection of two datum planes. People always want to know where datum plane B is. There is no datum plane B. Datum feature B establishes two datum planes, which are the second and third planes of the datum reference frame. If you think there has to be a datum plane B, get over it. When people understand the terms correctly, GD&T becomes a lot clearer. Make certain the folks doing the training are using the correct terms so your folks do not get confused. We use the correct terms because at Techies, GD&T rules. I'll see you next tip. There's a lot of great technology today that is being underutilized or ignored. Much of it because geometric tolerancing is misused and underused. Drawings are changing. The ASME Y14100 standard defines a drawing as an engineering document or digital data file. I created this part by using CAD to make a digital data file or solid model of the part. I then sent it to our rapid prototyping machine, which made this part. Great! One problem. I have no idea whether this part is what I need. That requires measuring the part and determining if the features on the part are within the required tolerances. The technology exists to quickly and accurately inspect the part, provided I embed the tolerances in the digital data file. Only by taking this step can I assure that this part will fit and function in the assembly. My CAD system can generate a perfect part out to 24 significant figures. However, there isn't any processing equipment that can produce a part anywhere near that accurately. Using equipment like this, we can use point clouds of data from part measurements to merge with our digital data file and determine part conformance. This last step is only possible if tolerancing has been applied to the features in the digital data file. The software that evaluates the data should then be compliant with the ASME Y14.5 and the math standard Y14.5.1. Most engineering colleges are not teaching geometric tolerancing, so they graduate engineers who are pretty good CAD jockeys but do not know how to tolerance. They get jobs where they sign off on drawings that they can't read. Any finite element and tolerance analysis they perform is inadequate if they do not know how to take the part variation into account. When I train, I first wear this shirt that asks the question, "Got tolerance?" to make people aware of what they do not know. Later in the training, I switch to a shirt or hat that says GD&T rules, because if you are viewing this tip, you know it does. Let's work to create an awareness that without GD&T, the new technology will not work. That's what we do at Techies, because around here, GD&T rules. I'll see you next tip. There are many default rules found in Section 1.4 of the Y14.5 standard. When you reference Y14.5 on a drawing, you invoke these rules. Rules like features must be toleranced, 90-degree angles apply if the lines are depicted at right angles, dimensions and tolerances apply at 68 degrees Fahrenheit, and so on. If you do not want a rule to apply, you must do something overt on the drawing to override the rule.
Here's an example of a fundamental rule and how it may be overridden. It is Fundamental Rule 1.4M. And it tells us that unless otherwise specified, all dimensions and tolerances apply in a free state condition. In other words, the default is that the parts are considered to be rigid. You're not allowed to distort the part in any way during verification. You can't just look at a part and say, oh, that's a non-rigid part. You have to look at the drawing and see if it's been specified otherwise. If not, it's considered to be a rigid part. This sheet metal part is considered to be rigid because I've referenced the Y14.5 standard. As soon as I did that, All of the fundamental rules are in effect unless I specify otherwise. On this drawing, I have specified otherwise. We see that dimensions and tolerances apply with the part restrained to datum feature A simulator with 10 newtons applied to each datum D target. Now datum feature A is the bottom of these two tabs, and so the simulator would be a nice flat plate. The datum D targets are two 7mm diameters, D1 and D2, and so I would apply 10 newtons in those two areas and then inspect the part.
If you make or read drawings, make sure you know the rules. If you need help with that, contact us, because at Techies, GD&T rules. The continuous feature symbol was added to the ASME Y14.5 2009 standard. Before the addition of this symbol, we didn't have a good way to apply a form control to a feature of size that had interruptions. Some people tried to accomplish this using profile of a surface. The problem that was using profile of a surface on a toleranced feature was not clearly supported in the standard. Here's the right way to control the form of an interrupted feature of size.
Usually in assemblies we like to have interchangeability of parts, but that's not always the case. In some hydraulic and pneumatic applications where you want a metal-on-metal seal, the parts are selectively assembled. In other words, they're matched. Let's say that this is a spool for a spool valve in one of those applications. I would make up several spools and try to keep them very cylindrical while I allowed the size to vary. Notice that the size tolerance is bigger than the cylindricity tolerance by quite a bit. Then I would grade the spools, and then I would match them up to bores, and then I'd do a pressure test to make sure that they're not going to leak. Well, we have a little bit of a problem here because cylindricity is an individual tolerance, and I really don't have one feature here. I have 5 features. There's 5 diameters because of the interruptions. So the cylindricity applies to those 5 diameters individually. This is showing you how long my cylindricity tolerance zone would be. So it's not keeping all 5 acting like one nice cylinder. It's keeping the individual cylinders acting like a nice cylinder, but no relationship between them. In 2009 we were given the continuous feature symbol, CF. Now I can add that, and it says treat those 5 diameters as though they were one continuous feature. If I do that and add a cylindricity to this, the cylindricity zone will apply to the entire length of those 5 features. So now, from part to part, the size may vary by as much as 0.1 total. But whether I have a large spool or a small spool, it has to be very cylindrical over the length of the 5 diameters. That way I can have very nice cylindrical spools, and I can match them up to very nice cylinders in the bodies to make sure that my valve will seal. Notice when I added the CF, the 5X went away because I don't have 5 features anymore. As far as the standard is concerned, there is only one continuous feature, ignoring those interruptions.
Once again, prior to the 2009 revision of the standard, notes were required to explain what we can now state by using the continuous feature symbol. The standard is evolving. Each revision gives us more tools to simplify and clarify the design intent on the drawing. Of course, the people making and reading the drawing need to understand these tools. This is today's print reading. If you or your folks need to learn how to properly apply the tools and read prints, contact us, because at Techies, GD&T rules. I'll see you next tip. You should always know what rules apply to the drawing you're reading. The rules in geometric dimensioning and tolerancing have changed over the years. In addition, the meaning of such symbols as runout, total runout, concentricity, and symmetry have changed. Reasons for these revisions include trying to be compatible with the ISO standards, changes in our technology, and the increasing complexity of new products. You cannot go by the drawing date since companies may delay adoption of a new revision for several years. Unfortunately, the drawing doesn't always state the revision to use when translating symbols into plain English. Often you can determine which standard was used by observing differences in the callouts. Your choices of Y14.5 standard revisions are 1966, 1973, 1982, 1994, and 2009. Here are a few things to look for when determining which revision of the standard to use. This slide shows the differences in the first 4 revisions of the Y14.5 standard. I explain these differences in detail if you view the video on our premium site that goes along with this tip. Or you can go to our tip page and study these differences at length. This slide is showing you the symbols that have been added as of the 2009 revision. Once again, on our premium site I explain these symbols. Don't use these little hints that I just gave you to determine the standard that the drawing was made to. You should always look for a note stating which revision of the standard was used to read the drawing. If you need help understanding or creating drawings, give us a call, because at Techie, GD&T rules.